So good morning.
Good morning. Very good morning, Dr. Wieland.
Yeah, morning. Okay, Mr. Sharma.
Yeah, good to see you.
Yeah. You are in Shimla or?
Yes.
Yeah, okay.
Very cold here. Maybe may not be as cold as in Switzerland, but it's quite cold.
Yeah, it is. Now it's about 6 degrees at the moment.
Yeah, we have about maybe 8, 9.
Oh, yeah, not so different. But we have rain. It's raining. Or it's rainy.
But no, for us it would rain tomorrow.
Oh, I see.
And maybe they say on 5th it may even snow. First
Yeah, we have snow 2 days ago and yesterday in the morning, but it disappeared within hours.
Okay. So, but for us it's very unusual that in first week we receive the snow.
I see.
Yeah. The other day, Dr. Chauhan was asking about you.
I see. Yeah. Yeah, we are exchanging some emails.
Yeah, probably you are. Yeah, he said that you have exchanged emails with him, and he was telling that you intend to visit India maybe sometime in future.
Yeah. I still want to go to HP next summer or next late summer.
Welcome. That would be so good.
It was very nice there.
Yeah. It's a good idea.
Yeah, no. Who'll start? Who'll just start with?
Sir, with your permission, shall we start?
Yeah, but I can see the number of participants is not very large. It's okay, we start.
Though it is the 60 registered participant we have, but the numbers are quite less right now.
How much?
19.
Start.
Shall we go? Or
Okay. I think let's proceed. Or if you want to wait for 2 more minutes, I can chat with Dr.
okay.
Wheeler.
Sure, sir.
Maybe you should, Dr. Wieland, you should plan sometime. I understand maybe October, September, or sometime in June.
I see. I was thinking of September or something like that. Next
September should be okay.
September should be okay.
Even June should be okay.
It's not the rainy season in June.
No, it's just onset of the rain. So July would be the rainy season. July, August, and sometimes the rainy season extends to September also. But the June would be much safer.
It would be safer. I just thought it would be good after a rainy season, for example. Yes.
No, it's before the rainy season, it is safer.
Yeah, it is safer. Okay, thank you.
So you see, like these hill slopes, they get saturated during the monsoon rains, and sometimes it's risky to travel in the hills during September.
I see. Okay. I have to think about it. Yes. Okay.
And these were the areas where they were not receiving rain earlier, and then all the fragmented soil sitting on the steep hill slopes, the contact of soil and overburden and the rock gets lubricated, and this whole hill mass start moving down. So there's sometimes there is a risk.
Yeah. Okay. Yeah, the hills are really steep. It is it's just steeper than ours.
Very steep. Yeah, your mountains are not that steep, you know. Here, these mountains are very steep.
Yeah, I've noted these roads. Yes, It was quite adventurous when I went there.
Your mountains are like Shimla, like the lower hills of Shimla. They are not as steep. But over there, if you move to Uttarakhand, Himachal Pradesh, the mountains are very steep.
We wanted to go to this Spiti Valley.
Yeah, sure. We'll organize. We'll organize, no problem. Just do let me know in advance so that I get all the permissions.
Yeah, I thought the permissions is probably a problem. Dr. Chauhan, he told me he may not be that easy.
We'll arrange it. No problem.
Okay.
Yeah. So should we start? I think already 5 minutes.
Yes, we should start.
Namaskar and a very good morning, distinguished guests, resource speakers, esteemed participants, ladies and gentlemen. My name is Kalpana from Committee for International Commission on Large Dam, India, INCOL. On behalf of INCOL, we extend a hearty welcome and sincere gratitude to today's resource speaker, Dr. Martin Wieland, ICOL Vice President and President INCOL, Mr. Devendra Kumar Sharma, Vice President INCOL and Member DNR, Central Water Commission, Government of India, Dr. R.K. Gupta, Secretary General, Mr. Aditya Kumar Dinkar, Treasurer Dr. G.B. Patel, our esteemed guest, and other dignitaries. We convey our sincere thanks to all professionals for their time and presence for today's virtual training on the topic on reservoirs triggers seismicity. May I now invite Mr. D.K. Sharma, President INCOL and Vice President ICOL, for the welcome address and opening remarks. Before he starts, let me introduce our President INCOL, Mr. Devendra Kumar Sharma, presently Honorable Chairman, Himachal Pradesh Electricity Regulatory Commission, has more than 40 years of experience in the energy and water resource sectors in India and abroad. He worked as Chairman, BBMB, and Managing Director of HPPCL. He has experience of working in the corporate sector in India and also in Tala Hydroelectric Project Authority in Bhutan. He has worked in SJVNL and in HPSEBL in various capacities. Presently, he is Vice President, International Commission on Large Dam ICOL and President INCOL. He has presented number of papers in international and national level. Now we invite Shri D.K. Sharma for the opening remarks, please.
Dr. Martin Wieland, resource speaker for this training program. Dr. R.K. Gupta, Vice President INCOL, Member Design and Research, Central Water Commission, Government of India. Mr. A.K. Dinkar, Secretary General INCOL. Delegates from different parts of the country, ladies and gentlemen. On behalf of the Committee for International Commission on Large Dams, India, INCOL, and also International Commission on Large Dams, ICOL, it's my proud privilege to welcome you all to this third virtual training course on earthquake and dam safety. This third course in the series is on reservoir triggered seismicity, which will be presented by Dr. Martin Wieland from Switzerland. Earlier two courses were also presented by Dr. Wieland, and they were on seismic aspects of dam design and earthquake and dam safety. And these courses were held in the months of September and October this year. Safety of dams and their potential risks to the downstream region, particularly in seismic active areas, are serious concerns for governments, private owners of dams, and affected communities. The complexity in design of dams increases with specific consideration is to be given when specific consideration is to be given to seismic forces. There has been rapid advances in the technology in the shape of seismic design practices. Virtual training course will provide you an overview of the possible effects of reservoir-triggered seismicity on safety of large dam projects. The first case of reservoir-triggered seismicity was observed after construction of Hoover Dam in US in the year 1935, and the lake bed which is formed because of the construction of the dam, the RTS was observed in that lake. Since then, over 100 cases of reservoir-triggered seismicity have been reported from all over the world. In the past, terms induced seismicity was being used to describe these seismic phenomena, but as seismicity is usually associated with tectonic processes, the correct term used in connection with large dams and reservoirs is reservoir-triggered seismicity. This is important because you cannot think that the reservoirs, they create earthquakes. You will find, if you look at it and go to internet, go to the literature, have literature review, you will find hundreds of papers written on reservoir-triggered seismicity. Because the largest RTS events cannot be predicted, which is hard phenomena similar to earthquake prediction, RTS has become the preferred dam safety topic for people opposing large dam projects. As dam engineers and owners, we are not familiar with RTS in the past. It was addressed by introducing a separate load case for dam design, which was called induced seismicity. This term is still used in some projects. Induced seismicity is still in the use because in the earlier literature, it was used for a long time. And as you know, it takes very long even for such terminology to become obsolete and gets replaced. State of knowledge on reservoir-triggered seismicity phenomena, including the physical process causing RTS and several case studies, is discussed in ICOLD Bulletin 137. In this virtual workshop on rational assessment of RTS from viewpoint of dam engineers, the RTS aspects would be discussed. However, interest in the induced seismicity caused by fracking and liquid waste storage in the United States, as well as geothermal projects, has grown significantly in recent years. The underlying process of these types of seismicity, that's cracking due to increase in pore water pressure, are similar to that of RTS. However, the pore pressures applied in these projects are several orders of magnitude higher than those caused by filling of the reservoir. Strong earthquakes, which are suspected of being reservoir triggered, have occurred in reservoirs formed by Coinal Gravity Dam, which is located in Maharashtra, Hessing Fangkyang Buttress Dam, China, Kremasta Embankment Dam, Greek, Kriba Dam in Zambia. Since then, the general interest for this phenomena has sharply increased. The maximum magnitude of seismic events observed in these reservoirs were of the range of 6 to 6.5. As reservoir-triggered earthquakes tend to have shallow focus, the ground motion at site of Coinal Dam and Hessing Fangkyang Dam were very severe and caused cracks in both these dams. These two approximately 100-meter high dams were subsequently repaired and strengthened and are in operation today. Microseismic activity in reservoir region of Coinal and Hessing dams is still high. For example, in Coinal Dam, Nearly 100 earthquakes with magnitude greater than 4 and about 10 with magnitude greater than 5 have occurred since 1967. Ground motions caused by these earthquakes are of no serious concern for safety of the strengthened dam structure. RTS was mainly observed at large storage reservoirs with reservoir depth exceeding approximately 100 meters and reservoirs with a volume of over 500 million cubic meter, which tended to decrease with time after the first filling of the reservoir. In order to assess the implications of RTS on safety of large storage dam projects, it's necessary to have proper understanding of the current seismic criteria. Unfortunately, very few who question the safety of large storage dams under the effect of RTS know about it, and therefore unrealistic scenarios questioning the safety of dams are brought forward. Dr. Wieland will discuss with you in depth about the details of RTS and will explain you various phenomena which causes RTS and also what would be the effects of RTS on dam safety. With this, I thank you all and hand it over to the organizers. Jai Hind.
Thank you, sir, for the thoughtful and illuminating address and giving the brief historic details and the importance of the subject. Ladies and gentlemen, now may I invite today's resource speaker, Dr. Martin Wieland, for the presentation. Let me introduce briefly about the speaker. Dr. Martin Wieland has been the chairman of the Committee on Seismic Aspects of Dam Design of the International Commission on Large Dam, ICOR, since 1999. Until 2015, he was also the chairman of Earthquake Committee of the Swiss Dam Society. He is a senior dam and earthquake expert at AFRY, Switzerland, where he has been involved in the seismic safety evaluation of some of the world's largest dams and other major infrastructure projects. He was a member of the Structural Advisory Board for the Panama Canal Authority. He was also the advisor for the newly established Dam Safety Directorate of the Government of Ethiopia. During the last 40 years, Dr. Wieland has worked on large dam and major infrastructure projects in 35 different countries. He has been involved in over 150 large dam projects and has visited many more. He has received an honorary professorship from Hanoi University in China in 2002. He was a member of the board of directors of the Swiss Society of Earthquake Engineering and Structure Dynamics and the Civil Engineering Division of the Swiss Society of Engineering and Architects. He has authored 300 technical papers in the field of dam and earthquake engineering. Now I request Dr. Martin Wieland to make the presentation. Over to you, sir.
Yes, thank you very much for this kind introduction, and also Mr. Sharma, thank you very much for this excellent overview. I think you have told already all the important issues, so there is not much for me to tell. Okay, so good morning, ladies and gentlemen. It is now 6:50 in near Zurich in Switzerland. We have winter time, so it's for me it is 1 hour earlier than the previous one. I hope you can hear me, and I hope you see my presentation.
Yes, sir.
Okay, because last time you remember we had some technical problem, and I was not really aware. And I must say the last presentation, which actually I delivered, but you could not hear it. So I would also like to add it today. But as it was said, the presentations today and tomorrow will be on reservoir triggered seismicity and dams on faults. because the reservoir triggered seismicity is also directly related to tectonic faults. Now, just to give once more a brief overview of the online training courses from September to January. Okay, 2 courses were already held in September and October. This course on reservoir triggered seismicity, it was originally planned for November, but it coincided with the ICOLD annual meeting, so therefore it had to be postponed to early December now. And there will be 2 more courses, actually the next one in 2 weeks on seismic safety of existing dams, and in January on multiple hazards and other aspects. What we discuss today are basically 2 bulletins which have been prepared by the Committee on Seismic Aspects of Dam Design. And I would just like to mention, in a previous presentation, basically what has been presented is a state or are the guidelines given in a bulletin 148 and in bulletin 52. But today we will talk about bulletin 137, that is on the reservoirs and seismicity, is the title, but it is concerned about reservoir triggered seismicity. And the other one is the bulletin 112, which is called Neotectonics and Dams, but it is concerned with active faults in dam foundation. So basically, I will cover these 2 subjects, and these are subjects, I must say, which are of particular interest for dam engineers. It is not an issue which people doing buildings and bridges who are concerned with these aspects. Now, the presentations I'm planning to give today and tomorrow are as follows. First, I would like to give this presentation, and I will give some comments on seismic waterways in reservoirs, because there are quite some misunderstandings about these waterways. Number 2, I will then talk about dam safety aspects of reservoir triggered seismicity. Number 3, I will talk about seismically active faults and discontinuities in dam foundations and reservoirs. Number 4, I will talk about design aspects of Rudbar-Lorestan Dam in Iran, which is located in a narrow canyon with multiple faults and discontinuities, which could be activated during strong nearby earthquakes. And number 5, I will like to say a few words about innovations for a dam on active fault and high reservoir sedimentation hazard in the Himalayas. And the last one, okay, we will see that. I will say something about dynamic stability analysis of a gravity dam subjected to the safety evaluation earthquake ground motion. This is also a subject, let me say, which could not be delivered during the previous workshop number 2 due to the technical problems which we encountered at the end of the second day of this seminar. Now, let me say a few words about seismic waves in reservoirs. Now, water waves in reservoirs may be caused by the following seismic hazards. Please keep in mind, number 1, it is a ground shaking, and as I mentioned already repeatedly, ground shaking is basically the hazard which is considered by all engineers and which is addressed in all seismic guidelines and codes. Okay, ground shaking in a reservoir, it could cause reservoir oscillations, and it would cause what I call sloshing motion. That is due to the vibratory effect of the earthquake effects. Number two, if you have mass movements into the reservoir, this may create important impulse waves. I think this is the most important issue. Number three, if we have a fault in a reservoir, the vertical offset in a reservoir may cause something which has been observed in some very strong earthquake. It is like a tsunami. It is a vertical offset of a fault, so this would be faults passing through reservoirs. And number four, we could have, due to non-uniform ground movement in a reservoir area due to nearby fault ruptures, which may excite the fundamental, let me say, sloshing vibration of the reservoir. These are quite exceptional cases, but I would like to give here an overview or a brief overview based on examples of these four types of waves. Okay, here is a typical reservoir in Switzerland or at the Italian border. I have shown it once. You see here there are some, let me say, slopes where some debris is falling here into the reservoir. This is already Italy here. The photo is taken from the Swiss side. So we'll talk about water waves in such reservoirs due to seismic effects. Now, last time I have given a brief introduction into structural dynamics and to discuss water waves oscillations in the reservoirs due to ground shaking. It is very useful to make use of this, let me say, diagram, what I called dynamic amplification of a single degree of freedom oscillator, because if we consider sloshing motion and if we consider the lowest mode, this is basically can be represented by a single degree of freedom oscillator. Now, if we look in this diagram, if we look into large reservoirs, and I will give an example, the excitation, the natural frequency is very, very small. And from the earthquake ground motion, we know that the frequency of earthquakes is in the range maybe of 2 hertz to 5 hertz, but those of a reservoir may be only 100th of a hertz, can be several minutes. So therefore, if we would look in this diagram, which shows the excitation frequency, that is the earthquake, 2 to 5 hertz, divided by the lowest eigenfrequency of the reservoir, which is maybe 0.001 hertz. So we will get here a ratio which is not 3, but is about 100. And if we are at 100, you can see here the dynamic amplification factor will be extremely small, and it will also be, as you can see here in this resonance curve, we have given here the dynamic amplification for different damping ratios, and we know the damping in water is very small, say almost 0. But once we go into very large numbers, like reservoir oscillation, you see the effect of damping in a reservoir is not important here. So what we can see is if we have reservoirs, the acceleration accelerating the whole mass of a reservoir is extremely small for large reservoirs. So therefore, we can conclude basically that the water waves in the reservoirs due to ground shaking, that means due to the ground acceleration, are actually very small. So we could understand it based on this simple diagram, but I will show some example. So the motion which we are considered basically is what we call sloshing motion. There are some, let me say, explanations or closed form solution for a square swimming pool, for example, how we can calculate the eigenfrequency. This is the frequency in the radians per second, how we can calculate it in a closed form. But what we can see is the eigenfrequency of the sloshing motion, and we consider here we have different eigenfrequency. If you take the first eigenfrequency, that means n equal 1. We can see that because this will be the dominant one, that eigenfrequencies will only be relatively large if we have small reservoirs. That means, for example, a swimming pool. If we have a swimming pool, and if I go back into a previous diagram, in a swimming pool, we could be at this, we could be here somewhere. So therefore, we have quite large sloshing motions during strong earthquakes. The same is in liquid storage tanks, which have only diameters of 10, 20 meters, not more. But in reservoirs for dams, we have characteristic dimensions which are, let me say, corresponding to the crest length of several hundred meters. So therefore, let me say, the eigenfrequency is, of course, much smaller. So please note that based on this, actually large sloshing motions in reservoirs due to seismic effects only occur in small reservoirs, basically tanks, which are not relevant for dams, if I may say it like that. So for the ground acceleration, it does not create large, let me say, waves in the reservoir. Now, I have shown this photo before. This is a photo from Coinal Gravity Dam in Japan, and here the Japanese, they have strong motion instruments at the base here in a control gallery and on the crest. And in addition, they measured the water, let me say, water depth in a reservoir. And this dam was subjected to a magnitude 6.7 earthquake, which is, I would say, is quite a strong earthquake, because the ground shaking recorded here at the dam body was about 0.5 G. So 0.5 G is quite a large number, but I would say it would also be a representative for the dams in the foothills of the Himalayas. So from the water level measurements, you could see this kind of, after the earthquake, this free vibration of the reservoir, which was subjected to 0.5 G, which is a high value. And you see here the maximum amplitude is 6 and the minimum is 4. So the wave height, and this is in centimeters, the wave height is 10 centimeters. So during a strong earthquake, you have only very small water waves, which is contrary to, as I would say, water tanks and swimming pools where this water wave for the same earthquake could be 1 meter. Okay, but in large reservoirs, this is very small, and we see here from this free vibration oscillation. If you do a kind of a Fourier spectrum calculation, you will find that the eigenfrequency here is about 6.5 minutes, is about 400 seconds, and the eigenfrequency here is 0.0026 Hertz, and the damping ratio, which gives this decay with time, is about 2%, and the reservoir is oscillating, as you can see here, even 2 hours after the earthquake, whereas the duration of the earthquake was only maybe less than 20 seconds. So the reservoir will be oscillating slightly after the earthquake for quite some time, as we can see here, for about 2 hours. Okay, this is for the ground shaking is the first mechanism. So ground shaking, I would say, is not a problem for large reservoirs. But the main reservoir which we have in mountainous regions are landslides. This is a photo from Lake Saras in Tajikistan. This dam was basically created by an earthquake in 1911, where a big landslide blocked a valley and created a large lake, which is still there today. Very large lake, but in the reservoir area, this is located in the Pamir mountain range. And as you can see here, some geologists, they have marked some other potentially unstable masses with volumes of several 100 million cubic meters, which could be triggered, for example, again by a strong earthquake. Pamir Mountain is also an area of very high seismicity, like the Himalayas. So if we have this sliding of this several 100 million cubic meters into this reservoir, which is also a very deep one, is several 100 meters deep in this valley, it would create a big wave. It would create what we call impulse waves. Of course, the impulse wave will be maximum just opposite of this landslide. It could, the water wave could come up 100 or more meters, depending on the velocity which this mass would hit the reservoir. But the dam is here, or it is a natural dam, is on that side. So therefore, the wave action, let me say, perpendicular to the impulse direction, of course, is much smaller, but it would still be very significant. So here we will talk about water waves, which can be tens of meters or even 50 meters or even more. This is very significant compared to the water waves due to ground shaking, where we talk only in a range of a few centimeters. So landslides, mass movements into the reservoir is the most dangerous, let me say, hazard. And these landslides, of course, may be triggered by strong nearby earthquakes. So the other issue I would like to talk is about dams located near faults. This is a Epcon dam. It's an earth dam here. It was built in the 1920, and it has, as an impervious membrane, it had a concrete wall. Here in the core, let me say, it is not a core, it is a concrete wall, unreinforced concrete, and we see here the reservoir of the Epcon Lake. Epcon Lake is just outside of Yellowstone National Park in Montana in the US. What can we see here? Overview. And in this reservoir, during an earthquake, magnitude 7.5 earthquake, in 1959, there was a big sage, a big water wave, oscillation of a whole reservoir was created, which then overtopped this dam. It overtopped it several times during a few minutes because the oscillation, if you have the oscillation of a reservoir, as I've shown in a previous one, it could be, just to remember here, we see here from this Kasho Dam in Japan, the natural period of a reservoir was there about 6.5 minutes. So therefore you have to imagine if we have here a wave, now a big wave, big amplitude wave, it will overtop during a few minutes and it will move back and come back because the damping of this, let me say, sage is relatively small, as we have seen. So several overtoppings have occurred during that earthquake. During the earthquake, also the dam settled, and the concrete wall, which is now, this is a recent photo here, the concrete wall protruded then because the dam body settled by about 1 meter, but the concrete, of course, remained unchanged. Now, I would like to discuss here briefly this Epcon Lake because it is, I would say, it is the only example where big water waves, seismic water waves, have occurred in a reservoir which have overtopped the dam crest. And we know, of course, overtopping of embankment dam is much more dangerous than overtopping of a concrete dam. We see here an aerial photo after the earthquake. This is a dam here, and we have a spillway here. Okay, and it looks like the reservoir is here, and you could see here probably this is a fault passing nearby. It just passes by very closely to this reservoir. This magnitude 7.5 earthquake basically occurred here. And you see here, there was a vertical offset along this fault here of several meters, and you can see here also that there are quite some deformations near this fault. Okay, it is I think it is very obvious. You can see here, it is not just a vertical offset alterated body, but it gives here some deformations. And if I go back here, okay, this is this fault scarp. It gave here some deformations and here some deformations. So the ground here, let me say the ground moved vertically, and due to this vertical movement, let me say non-uniform, it not just only moved here by, let me say, 4 meters, which was this fault scarp, but it also moved, let me say, in a non-uniform way near the reservoir, and then it involved the reservoir. So therefore, due to the ground displacement, which has a, let me say, a very slow period, the oscillation, the natural frequency of the reservoir could be excited, which is not possible by ground shaking. So this is due to ground movement. This reservoir, the oscillation in the reservoir could be excited, and which caused then this, what we call in the literature, you find it under the name of sages. So many people talk about sages when they talk about waterways, but sages, I must say, it is only this example which is reported, which is important, and it is if a very strong earthquake occurs near the reservoir, as in this case. So if I doesn't move somehow. So, okay. So we see here also again from Epcon Lake. This is after the earthquake. This is, you see here some trees from the overtopping. Okay, you don't really see the concrete wall, but you see here a spillway, and there has been some overtopping here, some damage occurring in this canal lining. And I would like to draw your attention to this opening. I think it is an ungated spillway. Usually these are considered as very safe. But when we look the size of this opening here, it is only maybe 3-4 meters each opening. This is by far too small. So if you would have here a major flood, and we have seen there in Epcon Lake, you also have some landslides into the reservoir, which bring in some floating trees. It would block this reservoir, this spillway. So we could say this spillway here is unsafe. It has been modified in the meantime, but there are quite a few dams with free flow spillways. It's like a culvert with a small opening, and if you have a small opening, it can be blocked very easily by floating debris. That is just a side comment, but I would also like to mention, once the whole reservoir will oscillate, will slosh, and over top, you cannot prevent it by the spillway, because it's the whole mass of a reservoir which oscillates, so the spillway will provide only a small damping. It is not essential. And the last picture I would like to show here is this strong earthquake. It had triggered a landslide here, a mass rockfall of about 38 million cubic meters, and it has created a landslide dam. It is still here now. This is a recent photo. The road even passes through this landslide. I visited this area a couple of years ago, and but I have not even noticed when I drove here that he drove over this landslide dam. But what you can see here, this landslide created this reservoir, and this reservoir is still there. It is called Earthquake Lake. So I would also like to use this example to show that strong earthquakes can create natural dams. And I think in the Himalayas, when I traveled quite a bit, also in north of Kashmir in Pakistan, and I think when we traveled along a river, I thought I have seen many locations where such landslide dams have occurred. Also in Iran, I have seen plenty of them. So to sum up this introductory comment is that large water waves in the reservoirs are created by mass movements into the reservoir. This is a main concern for water waves. Somebody called this impulse wave tsunami. Okay, we call it usually impulse waves. It is not the ground shaking which creates the large oscillations or water waves. The exception was this Epcon Lake, as I said, where due to the proximity of positive fault and due to the non-uniform ground motion near that fault, ground displacement in this near this fault, it was possible to excite this this sage in this dam. Okay, but people like to talk. I have seen in many discussions, people like to talk about these water waves in a reservoir, and it is quite, I feel it is important to have a clear idea about the possible sources of such waves. So I would like to go, this was my introductory comment, and I would like to go now to the main subject, which is reservoir triggered seismicity. And here I will talk, when we talk about reservoir triggered seismicity, I would like to talk about the implications of reservoir triggered seismicity on the dam safety. I think that is basically the main concern of the dam engineer. Okay, it was already mentioned, Mr. Sharma has given, of course, very nice introduction, and he has covered already the important issue in a very condensed way, but he has addressed all the important aspects of reservoir triggered seismicity. I would just like to repeat some of these issues about the official ICOL terminology. We have the old, I would call misleading term, where people talk about reservoir-induced seismicity. It is misleading because some people may believe, and I think especially those who are critical about dams, that by filling a reservoir of a large dam, you create earthquakes. This is a wrong perception. The right term which we have adopted in ICOL is, the term is not induced, it is called triggered seismicity, because we have already, it's like with landslide, we have some mass, for example, unstable mass, and we need a trigger that this mass starts to move. And that is the same with earthquakes, with faults, with tectonic earthquakes are basically a result related to faulting. So the proper term we use in a dam, let me say in a dam safety problems is reservoir triggered seismicity. But I have seen still many people like to use that. Don't use it. It is not correct. You should use it. It invites people here to focus on such kind of issues, which is unnecessary. It is triggered. Now, as I mentioned, RTS, this is a short form, is used for triggering tectonic events due to reservoir impounding and operation. So we talk here basically for dam safety. We are interested in the strongest earthquakes, and the strongest earthquakes are of tectonic nature, are tectonic earthquakes. However, we have now, let me say, an increased discussion on induced seismicity, and the induced seismicity, for example, in the case of dams, may be due to the collapse of underground cavities in the reservoir area, and induced seismicity is related to hydraulic fracturing. Basically, in the fracking industry now, you see in the US gas and oil extraction, people are using this hydraulic fracturing technology, and this basically with that, you may trigger already earthquakes, which otherwise may not be triggered, or may only be triggered in a near future. So if we talk about induced seismicity, it is by basically by the gas and oil industry, and also in the US, people have pumped waste into the underground, and also for geothermal projects, you have to use hydraulic fracturing in order to increase the surface of the circulating water, which are used for warm water or steam generation. So where hydraulic fracturing is being used by imposing very high pressures of, let me say, several hundred bar. Okay, moves. Okay, I would like to mention here now ICOLD has addressed this issue on reservoirs and seismicity, and this is in ICOLD Bulletin 137. You should be able to get access to this bulletin if you are a member of INCOLD. So you should get a free copy there. Let me say the different aspects of reservoir triggered seismicity are discussed, and it is not a guideline here, but we have given the title State of Knowledge. That is based on the experience up to when. This is a kind of a summary, but it is not the final knowledge, let me say, about reservoir triggered seismicity. Now, of course, the basic question which comes up is reservoir triggered seismicity a safety concern for large dam projects? This is, of course, an important or is the most important question which we have to ask. And I'm trying to explain that in a following presentation. Now, what are the basic requirements for reservoir triggered seismicity? Mr. Sharma, he also mentioned that, like earthquake prediction, the prediction of reservoir triggered seismicity, and especially the strongest events. I must say, if we talk about prediction, we are basically interested in the prediction of the strongest events. We are not interested in very minor events which do not cause any harm or which do not disturb any people or which cannot even be felt, but which can only be recorded. We are not interested as engineers, we are not interested in such events. We are interested in the strongest events. And I would like to mention earthquake prediction means to predict the strongest events, predict the time, and to predict the location. There are three main factors which are necessary. Otherwise, if you are unable to, let me say, to define these three factors, you can also not do any alarming of affected population. You may read in the newspaper some geologists or some other people make a prediction that there is a probability of 50% that in the next 100 years a magnitude 7 earthquake occurs at a certain location, for example, in the Himalayas. Okay, if you have such kind of information, basically politicians and so on, you cannot do anything. Okay, you have to make your dam project safe, but you cannot save or you cannot evacuate people. So please keep in mind when we talk about earthquake prediction, we talk about the strongest events which can cause some harm to people. Okay, now what are the basic requirements for RTS? They are, number one, existence of active or potentially active faults. Okay, so therefore I'm also talking here in this presentation on faults, because it is if you have these faults, then you may have this problem of reservoir triggered seismicity, and or in areas where there are faults near failure limit, that means regions with high tectonic stresses. So high tectonic stresses we have noted, or I just participated in a meeting in Brazil. In Brazil, people think they basically have no earthquakes, like maybe in some parts of the Indian subcontinent, but they had a lot of, let me say, volcanic activities. So they were from cooling effects and so on. So therefore, they have their high tectonic stresses, and most of the seismicity in Brazil is basically related to this problem regions with high tectonic stresses. And there are quite a few dams there, quite many, I would say, large dams, where reservoir triggered seismicity has been observed. So somebody came to the idea to make a seismic hazard map based on reservoir triggered seismicity observation. I said, okay, that is of course a wrong approach because the reservoir triggered seismicity tends to decrease with time, so it is not really a basis for, let me say, seismic hazard assessment, which is a basic for the ICOLD guideline on selecting seismic parameters for the design of dams. So, problems. Okay, it was also Mr. Sharma mentioned there are over 100 cases where reservoir triggered seismicity has been observed. This is just a list which we took from a publication from the US on reservoir triggered seismicity. It shows basically that reservoir triggered seismicity is a worldwide phenomenon which has occurred in many countries, as you can see, on all continents: Australia, Brazil, USA, Zambia, Thailand, and so on. And we see here a number of names of reservoir, but the important issue is what is given here is a magnitude or the intensity of the strongest event. And as I said, for dam safety, we are interested in the strongest event. Okay, we are basically magnitude 3, 4, 5, some, again, 5, 6.3 is a big one, is in the Kariba, is in Africa, is in a Rift Valley, okay, it's in the Eastern Rift Valley. It's a strong earthquake. The reservoir also being very large, actually one of the largest in the world, 160 billion cubic meters. And the arch dam is 122 meters. So 6.3, which occurred here. If I go further up, I don't see here anyone in India yet. If we go here, okay, here we are. You see the Coinal is also listed here, about 100 meters high, reservoir 2 billion cubic meters, magnitude 6.3. Here in 1967, Kremasta in Greece, an embankment dam. This is a gravity dam, also magnitude 6.3. And we see here also in Greece 5.8. Oroville in the US, where you just had recently a problem with the spillway safety, which created some problem, but there was also quite a strong reservoir triggered earthquake. There are some other strong ones, even in Thailand when I was there, and I have even felt that in the Bangkok area is a magnitude close to 6. And there is this famous one, which was also mentioned in China, Xinfengjiang, is a magnitude 6 earthquake, because this earthquake, Xinfengjiang, I will discuss it, and the Coinal earthquakes are earthquakes which created damage to the dam with magnitude 6 and 6.3. Okay, the Coinal dam, okay, there is some controversy usually with these strong earthquakes, because it is quite obvious that the dam owners, they contest let me say, the claim that such a kind of an earthquake may be due to filling of a reservoir, but there are, on the other hand, geologists or earth scientists who are convinced, let me say, that it is earthquake triggered, but where basis of evidence that it is earthquake, that a reservoir triggered is usually quite small. So it is more a hypothesis, but at this time, and I must say, the former ICOLD president, Varma, he was very much opposed when somebody told that the Coinal earthquake being a reservoir triggered earthquake. Okay, we as ICOLD, we do not say that. This list I'm giving here is just a list which has been published elsewhere, but I wanted to use this case to explain that it becomes quite difficult if you have stronger earthquake to explain if this earthquake is actually triggered by filling of a reservoir or if it would have occurred anyway, you know, just maybe at some other point in time. So this is still a big problem, and I would say I will give an example here on this issue. But 6.3, this is the important point you have seen. There are about 3 earthquakes with magnitudes in the range of 6.3. Maybe somewhere people say 6.4 or 6.1, but it is about 6.3 in that range. But 6.3 is quite a strong earthquake, and as you know from Koina, there is also a village, Koina Nagar, I thought, where quite a large number of about 100 people were killed in their buildings because they were not designed against earthquake. So this is this list. Now, what are the main features of RTS? Just to go back to this list, as I mentioned, RTS, they may occur everywhere, and it is, as I mentioned, it is basically not possible to predict the magnitude of a maximum event, and even to predict if such seismicity will occur. So people are suspecting, for example, that maybe some seismicity may occur in certain types of reservoirs and in certain seismotectonic regions. Now, what are the main features of RTS? It is number one, the seismic events during and after impounding are more frequent than background seismicity before impounding. Background seismicity would be the natural seismicity, but due to impounding, you may have more frequent or even some stronger earthquakes. Number two, with the increase of reservoir level and variation of water level, the number and magnitude of RTS in events increases. I think it is the Aswan Dam is such a case in Egypt, where due to variation of the water level, which is actually quite small, it's maybe only 10, 15 meters. In Switzerland, we have variation of reservoir levels of 60 or 100 meters in very high dams. But in Aswan, it is relatively small, but there are in some areas, people have recorded some seismicity and tried to keep some correlation with reservoir level and the rate of increase of reservoir level with seismicity. And as Mr. Sharma mentioned, a large number of earthquakes have been recorded already at the Coinal Reservoir area. I don't really know how large the, let me say, seismicity was prior to the earthquake, because I think no records exist. Number three, often RTS events decrease towards background activity after peaking. Therefore, I said, like in Brazil, as somebody wanted there, they are not a problem for existing dams, okay, or let me say older dams. It is basically an issue of new dams. If a dam has been there for 50 years, it is, I must say, it is very, very unlikely that you have some seismic event which can be due to reservoir triggered seismicity. So the background, the events decrease as a function of time. Now, if we look based on the list which I've given previously, if somebody wants to make a small statistics, what is the frequency of reservoir triggered seismicity? In the previous list, we had about 6 earthquakes with a magnitude larger than 5.7. The number of dams with a height larger of 100 meters worldwide at that time was about 400. And therefore, the probability of RTS with a magnitude larger than 5.7, and for a dam larger than 100 meters, conditional probability would be 6 events divided by 400, makes 0.015. So you could say if you have over 100 meter high dam, purely from a statistical analysis, you have about a 1 to 2% probability that you may have a reservoir triggered earthquake with a magnitude larger than 5.7, and 5.7 may be already, let me say, a dangerous earthquake for poorly constructed dams. But a magnitude 5.7 is certainly not a problem for a well-designed, well-constructed, and well-maintained dam. So, but it is just given here, you have quite some probability. It is not a problem for the dam, this kind of earthquakes, but as we have seen in the case of Gandhinagar, in Coinal Nagar, where a significant number of people were killed in the buildings because the buildings were not able to withstand this magnitude 6.3 earthquake. But for dams, it should not be a big problem. But what I want to say is a probability of 1 to 2% is not a negligible value, so we have to take care of that. Now, which were the large dams subject to really strong RTS? It is the Xinfengjiang Buttress Dam in China, 105 meters high, 1962, magnitude 6.1 earthquake. Dam was damaged with some cracks, longitudinal cracks near the crest, and was strengthened subsequently. And also the seismicity here at this location is still very high. People have recorded more than 100,000 events, but they are very small events. The second event is a Coinal Gravity Dam in India. I would like to say buttress dams somehow are also a little vulnerable against earthquakes. Nowadays, I would say people do not build buttress dams. It is too labor intensive. People build RCC gravity dams, but not buttress dams anymore. But in the 50s, 60s, and so on, people were keen in building this kind of dams. Now, Coinal Dam is about the same height. It was subjected to a magnitude 6.3 earthquake in 1967, and also the dam was damaged and it was strengthened. I will show it briefly. When, as was already mentioned by Mr. Sharma, the Hoover Dam is very high, 220 meters high, which experienced the magnitude 5 earthquake. It was not a safety problem for the dam, but you can feel it. Kremasta embankment dam in Greece, 6.2, 6.3. I'm not aware of any damage. Kariba Arch Dam in Zambia, also a very strong earthquake, magnitude 6.3 in this Rift Valley, and people are building some more dams in this Zambezi river valley, where you will have somehow an increased seismicity. So if you build, for example, a dam along the Zambezi River in this Rift Valley, and we were involved in one project, and we have to predict or to estimate the upper bound of a reservoir triggered seismicity, and we basically have to assume an upper bound of 6.3, just because this Kariba Arch Dam event occurred there. Now, if we look in these events here, the maximum magnitude suspected, and I write it like that, suspected of being caused by RTS are magnitudes in the range of 6 to 6.3. Maybe the upper bound is about 6.3, but as I pointed out already in the case of Coinal, people are questioning that, and the dam owner is against, of course, very much against claims that this event was caused due to impounding of a reservoir. It is clear why no dam owner wants to be responsible for that, because let me say, if you have some people like in Coinal Nagar, where people get killed when people ask for compensation. So it has some legal aspects. Okay, so it is really not a simple issue from that point of view. Now, what I mentioned already, the maximum observed or suspected RTS magnitude is about 6.3. And the question is it possible that stronger earthquakes could be triggered? Because for the safety evaluation earthquake, safety check of dams, as I've explained during the previous workshop, we have to deal with stronger earthquakes. We have to deal with the worst case earthquake scenario, which involves basically even much stronger earthquakes. The Himalayas, even in Switzerland, we think upper bounds in some areas is maybe a magnitude 7. So, and in the Himalayas, you can have some earthquake magnitude 8 point plus. You can have very large. So therefore, the question is, is it possible that due to impounding of a reservoir, such strong earthquakes could be triggered, but based on because if such a strong earthquake occurs, it must have there must be some trigger, because if something is very close to failure, a fault, for example, it needs only some small trigger that this earthquake actually starts to occur. Of course, this you cannot predict, and the trigger could be only a very minor event, but it could also be some buildup of pore pressure. But it is based on the experience, and we have now in the meantime, since the 1930s, already for more than 80 years, we have not observed cases where I would say, the so-called upper bound or the maximum credible earthquake has been triggered. So at this time for RTS, we assume that the upper bound is about 6.3. But the event where we got a lot of discussion on RTS is the Wenchuan earthquake in China. Wenchuan earthquake, you know, is an important event 13 years ago. It's about 86,000 people killed. This is huge, you know. It is a magnitude 8 earthquake. And the question came up after the earthquake, because if some earthquakes occur, people get killed, governments being claimed for not providing safe schools, not proper planning, and then, of course, people who suffer damage, they also look to some culprits for these earthquakes. And in the case of the Wenchuan earthquake, there was Tipingpu Reservoir close to this epicenter of that earthquake. It was a dam which was completed just about 2 years before that earthquake, and it is a very high concrete face rockfill dam. So the question came up in the press, was this earthquake triggered by the reservoir stored behind this Tipingpu concrete face rockfill dam? And it was then published because there was some, let me say, earth scientists came up with a hypothesis. I must say it was purely a hypothesis. It's no, I would call it is not real science. And they came up with the hypothesis that you fill that reservoir and the earthquake occurred, so therefore it must be a reservoir trigger. Okay, it is not proper, let me say, science, what is being done. If engineers would do their design based on such hypotheses, they would end up in jail, basically, if you make such kind of statement. But the press has taken it up, and you have to see afterwards, after this geologist made that claim, even the Wall Street Journal published an article on that. Okay, scientists linking China's dam to earthquake, and it starts again this debate. So therefore, this case was then, or articles appeared in the press worldwide based on this article in a Wall Street Journal, and there are some others. One, the human trigger for the great quake of Sichuan, pulling the trigger on the RTS. Okay, and I called, and I was already a chairman there, I arranged that. I led a mission to this Wenchuan earthquake area, to Tipingpu, about 1 year after the earthquake. We're about, let me say, a kind of a reconnaissance mission with 13 international experts and about 13 or 15 Chinese experts. And we discussed this case. And also, I must say, based on this discussion, even in the highly respected journal Science, an article appeared in that journal, and let me say, our committee, myself with my Chinese colleague, we were then able to reply in Science magazine that this earthquake was basically not due to impounding of a reservoir. But I would like to discuss this case briefly because it's an important one. I mentioned before the maximum magnitude was 6.3. The Wenchuan earthquake had a magnitude 8 or 7.9, and tens of thousands of people killed. You know, it's a very big issue. But just to explain a little the situation of this is a plant. Here is a dam site, and we have here some tributary. This is a reservoir, full reservoir, and we have here basically the fault at some distance, and it crosses here with river, small river which flows into the reservoir. And the epicenter of the earthquake, as you see here, is about 15 kilometers from the dam site at the depth of also about 17 kilometers. So there were different kinds of arguments that filling of a reservoir at this fault here, we can imagine if the fault plane is here, already before the earthquake, we had a groundwater table, which was basically already near the surface. Therefore, due to filling of the reservoir here, the groundwater table did not change a lot, only very minor. So the additional pore pressure which was generated in this branch in the area of the fault plane is very small because the natural groundwater table was already very close to that which is observed during full reservoir. Okay, so that is the situation here. Now, people, because this is a big reservoir also, people have installed a microseismic monitoring system, and it is important, I must say, to record the natural seismicity prior to the earthquake. Here about 2000, starting pounding 2005, as I said, about 2 to 3 years before the earthquake. And you see, this is just the magnitude here, maximum magnitude observed prior to construction of a dam or prior to filling of a reservoir. And you see here, if you just optically look into that, we do not see any anomaly. But when in May, we have this strong magnitude 8 earthquake, which occurred here. So we have no sign that we have an increase in seismicity prior to filling of a reservoir. Also, the highest water level here in the reservoir occurred in 2006, 2007. At the time of the earthquake, basically the reservoir level or the reservoir was only 30% full. It was almost empty. But of course, if you have pore pressure to dissipate, it may take some time. In addition, here this is a maximum magnitude. What has been observed is in the range of less than about magnitude 4, about 4 and something. But if you look into the number of earthquakes, which is even on this slide here, you see prior to the filling of a reservoir, we have some natural fluctuations, starting pounding, it slightly decreased here, the number, but we can see here when the earthquake occurred at this location and afterwards the number actually also were let me say, not too different from what we call the background seismicity. So based also on, let me say, on many factors which were described when in a separate paper, the Chinese experts come to the conclusion that the Wenchuan earthquake was not triggered by the filling of Sipingpu reservoir. It is quite important, as I said, if somebody actually could prove that, let me say, this owner of this dam was responsible for killing 86,000 people. Okay, any company would get bankrupt, and it would have been a big impact on the dam industry, not only in China but even worldwide. So there was then, okay, I will mention later. Here it shows the filling of a reservoir which started about 2005, and it reached here maximum in 2006 and 2007, and there was the main shock here, magnitude 8, was then in 2008. Before there were some shocks, 3.7, 3.8, but as I've shown here, there were already several, of course, also 3.7, 3.8 for prior to impounding of a reservoir. Okay, so there is no clear correlation, as you can see, if you may remember the diagram before, between the reservoir level in this 3.2 reservoir and the size of the earthquake and the frequency of earthquakes. So, okay, what was the conclusion of our reconnaissance mission? Basically was there exists no evidence, let me say, that supports the assumption that this eventual earthquake was triggered by the Tipping reservoir. This is in short the conclusion which we have drawn. I would like to mention, of course, still people, let me say, the earth scientists, geologists, seismotectonics people, seismologists, they are still convinced, I must say, that this reservoir was triggered by the Tipping reservoir. It's the same like in the Coinal Dam. I must say the earth scientists, they are also convinced that the Coinal earthquake has been triggered by a filling of the reservoir of the Coinal Dam. We have to live with that. Okay, we cannot convince the people, the earth scientists, from their beliefs. But we, as engineers who are in charge of the dam safety, I think we have to take the corresponding measures. And we, I must say, we have better reasons, or let me say, to, or maybe not better reasons, but I must say, to argue against the claims which are based on some hypotheses by earth scientists, because they do not have any clear evidence to argue against that. Now, of course, in Tipping Dam, we thought if it would be really a reservoir trigger, there would be, in the coming years, people will find something new about this, or new reasons why this event was caused by the filling of the Tipping reservoir. So in 2018, there was a conference to commemorate the 10th anniversary of eventual earthquake, but no information was revealed which would support the claim that the earthquake was triggered by filling of the Tipping reservoir. So there, in these 10 years, I must say, people would have had time to do a research project, but people did not come up with new evidence that this reservoir was triggered by the filling of a Tipping reservoir. But as I pointed out already, still many earth scientists still believe that the earthquake was triggered by filling of a Tipping reservoir, however, without giving any evidence. It is purely based on some hypotheses, and where evidence is, as I said, very often in the press. It is before we had no dam, we had no earthquake, now we had a dam, we filled the reservoir, and there was an earthquake, so therefore the filling of the reservoir must be responsible for this earthquake. It goes that simple for many people, but it is not like that. This is a very important case, because as you see here, the magnitude of 8.0, it would be actually the magnitude of a maximum credible earthquake would have been triggered by this Tipping by filling this Tipping reservoir. it is, as I said, it is really a very important case. Now, if we look into some of the highest dams, the examples of reservoir critical seismicity is a Nurek Dam in Tajikistan. It's the world's highest, at the moment still, the world's highest embankment dam. There are two ones which are under construction, which are higher. One in Tajikistan is a Rokun Dam, which is under construction, and the other one is in China, which is also about slightly over 300 meters high. So now, what has been the damage due to RTS? I must say, if as engineer, if we have to answer this kind of question, we must also know what is the possible and what are the explanations of the damage which has been observed. Number one, Coinal Dam, as I mentioned, this is 103 meters high straight gravity dam. It has an unusual shape. I will show it then here because it was decided during construction to heighten the dam. Therefore, it has some unusual shape. And second one is in Fengjiang, Buttress Dam, 1962. In general, earthquakes are these earthquakes here, which cause this damage, are suspected of being caused by RTS. Because I said there is no clear evidence. I think the Chinese, they have probably accepted that it is reservoir triggered seismicity. In India, people are not of that opinion. Now, here in both dams, these earthquakes, which are near the dams, and they are shallow focus earthquakes, so the peak ground accelerations on the surface are quite high. Both dams developed substantial longitudinal cracking near the crest. And I must say the damage which was observed was attributed to design or construction details that would be avoided in modern dams. Hopefully people do not make these mistakes again. As I pointed out already, buttress dams are not in fashion, if I may call it like that, today. For concrete dams, people like to build RCC dams, which are massive gravity dams. And also one has learned a lesson here from a Coinal Dam that one should not deviate from the traditional shape of gravity dams which was used in the case of the Coinal Dam. But it is important that both dams were strengthened and are still in service today. So these dams were not damaged to the extent that they had to be decommissioned. So if we look now into the Coinal Reservoir, as Mr. Sharma has already mentioned, there have been a number of events with magnitude larger than 4 after the main event of 6.3 magnitude, and there were different periods of increased seismicity. What is shown in this diagram is the reservoir level here, and you see we have here some annual, let me say, cycles, operation of a reservoir, and you could see the reservoir was filled in 61, but the main earthquake occurred in 67, about 6 years after impounding of a reservoir, and afterwards, due to this reservoir fluctuations, you see the amplitude is about 40 meters, 660 to 620. So the seasonal fluctuation of a reservoir level is about 40 meters, and there have been some earthquakes, as you can see, in the subsequent years with magnitude larger than 4. But as it was mentioned already, the seismicity people record there still a large number of very small earthquakes which cannot be felt by people. So, but the important issue is that the number of earthquakes and also magnitude has decreased as a function of time, and it can be assumed that these magnitude 4 or magnitude 5 earthquakes are just natural earthquakes. It is a background seismicity, but since there is no data, seismic data, prior to the construction of the dam, it is difficult to explain if or to assume if these are events from a natural seismicity or if they have been some correlation with the reservoir. Okay, so therefore, if you do seismic monitoring, it is very essential to include the pre-construction phase in order to determine the natural seismicity. Now, what are some mechanisms? I would say the most widely accepted mechanism is the increase in the pore water pressure at the fault. We know that the strength or the shear strength of in a fault depends on the natural the normal stress times the friction coefficient, and the normal stress, it is the what we call effective stress. And if we increase the pore pressure slightly, the effective stress decreases, and if the effective stress decreases, of course the shear strength decreases, and therefore the buildup of the pore pressure may be the trigger of the earthquake. That is, for example, the case in hydraulic fracturing, where you impose very large additional pressures. So therefore, the shear strength of some faults, for example, becomes almost zero, and it may trigger some kind of earthquakes in some pre-existing faults. But what is shown here is also, depending on the depth, the buildup of the pore pressure at certain depth as a function of time. If you fill a reservoir, for example, and if you would check the buildup of the pore pressure at some depth, okay, this is a relation, the relative value of the pore pressure, the pore pressure as a function of the time divided by the imposed pore pressure. So you would see, for example, at 2.5 kilometers, the pore pressure will build up almost to the maximum within 40 to 100 days. At greater depth, for example, in Seeping 2 Dam, the hypocenter was at a depth of about 17 kilometers, even deeper, until this pressure would propagate actually really to that fault at 17 kilometers. It may take much longer period. As you can see, it may take a year, or it may take even longer. So please keep in mind also to build up the pore pressure at, let me say, at the hypocenter. It may take some time, and that will be an explanation, for example, why this earthquake here in Coinal has occurred after several years, and not just once the maximum was reached. But there are always, of course, a lot of discussions. Coinal, the focus was quite shallow, so it is not clear why it lasted that long time. Of course, also this diagram is a very schematic diagram because the permeability of a rock or the buildup of a pore pressure at greater depth depends on the geological and mechanical properties of this foundation rock. Now, to say something about the repair of Coinal Dam, the dam was basically damaged here. As I said, the shape is an unconventional because originally it was planned to build the dam probably at this height, but it was heightened during construction. So we have here this kink, and these kinks, or let me say with a negative curvature, if I may call it like that, they are points of stress concentrations. We have also stress concentrations here, and we have stress concentrations here where some damage may occur. And of course, due to ground shaking, we have amplification at this location. So therefore, cracks developed at this location at the dam. So after the earthquake, because of this longitudinal crack which developed, there were some repair by anchors, as you can see, which are anchored below the damaged zone. This was, let me say, repair of a damage, but afterwards, the dam was also strengthened. And you see here, there is a buttress was added at the downstream face, and this buttress has a slope, which makes this dam look like a conventional dam. The slope of 0.75 to 1. Usually for traditional gravity dams, you would use 0.8, but you have also here a small inclination of the upstream face. And the buttress which was added, it was a massive, a solid buttress here in the lower portion until elevation 1970, and in the upper, it was basically here this buttress, which did not cover the whole width of a block, which is about 15 meters. Okay, so the dam was basically repaired and it was strengthened, and strengthening means the dynamic characteristics of the dam have changed. If only people would only have done this anchors, if a similar earthquake would occur, it would still cause some cracks here again. But it would not be possible that this part will fall down. But there would be still some damage if you would only do this kind of repair. But by strengthening, you change the dynamic characteristics of the dam and you prevent basically that damage occurs again at this location. So I would say this is a good example to show strengthening, repair and strengthening of a damaged dam. Now, with RTS, what are the effects of RTS, not only dams? We must also look into the kind of a seismic hazard. I've shown this slide again, that due to earthquake, you can have different hazards. And one hazard is ground shaking, other is mass movement into the reservoir. You have fault movements, fault displacements. I would say fault movements and fault displacements in the reservoir would be very minor because the RTS events are generally small, so surface rupture will be, I would say, is almost zero. It's not a main hazard for RTS. However, we will have, in addition, the smaller events. If you have repeated earthquakes, it gives a sound of cracks, it gives noise. And we had a case in Switzerland where we built a dam, Contra, 220 meters high roughly, where due to stress redistribution, some cracking occurred with magnitudes of about 2 or 2.5, which are no problem to any buildings and had no effect on the dam, but it gave these cracks in the night and people could hear, and so they were disturbed. And of course, once you hear this kind of noise, people were concerned about the safety of a dam because it was related to the dam. Okay, so the noise, basically the three factors in reservoir triggered seismicity, which you have to consider, are ground shaking, mass movements, and noise. Okay, so I would like to discuss that briefly. Rockfall hazards at dam sites, because rockfalls could be triggered by RTS. This is very clear. Well, it must not be due to the strongest earthquake only. Okay, we see here some rockfalls. We see here some landslides near a dam, which was then overtopped. So therefore, we could say RTS could then create some landslides like that. Of course, RTS will not occur at such a run-of-river power plant because the head is only 20, 30 or so meters. So therefore, it will not be triggering RTS, but it just shows that smaller events could trigger actually landslides. I would like to use it here. Okay, if you have some landslides, what could be the consequence of such landslides? It could be that some rock falls on some arm of a spillway. As in this case, I have shown this photo again. This is the trunnion, the anchor of the arm of a radial gate, and where a stone here was falling basically on that arm. So we could say even a smaller earthquake, which could trigger a small rockfall, could basically damage gates of a spillway. Or due to rockfall, we could have damage of this steel plate as shown here, okay, of this gate. As you see here, depending on the location, it could also be a rockfall, even triggered by rainfall. If it falls down, it is a relatively thin steel plate, but it could, let me say, damage that steel plate. So this could be this damage pattern which is possible during RTS. I have also shown that this is the failure of a penstock, and if a failure of a penstock, of course, could also be triggered by a smaller earthquake, if, for example, this expansion joints would be damaged by a rockfall, or if some small movements would have been taking place. Or in this case, also you see the damage due to rockfalls in this powerhouse, rock falling through the roof of a powerhouse, and this portal crane, you see this gantry crane here, it was hit by a stone and it basically fell down. Okay. Here was then some damage due to flooding, due to the rupture of a penstock. Okay, so this kind of events, what I want to say is reservoir triggered seismicity could, also smaller magnitude, could still cause vast movements, landslides. Okay, This is a photo taken in this powerhouse, and it could damage its aqueducts, just some small landslide. It could block some tunnel entrances, as in this case, just some small rock falls. It could still damage transmission lines, like in Iran. Here, I just want to say this was also location of a seismic station, which was out of operation at the time of the earthquake. And as I said, the landslides, even under smaller earthquakes in some hazardous areas, as it was mentioned, like in HP, after the rainy season, you may have potentially unstable slope when they are fully saturated, so it needs only a small event in order to cause landslides. So therefore, what can we do? We do the monitoring, which is proposed. The monitoring of a reservoir is very important at locations for dams, I would say, with a height larger than 100 meters, or reservoirs larger than 500 million cubic meters, or where you suspect, based on the seismotectonics or the tectonic stress conditions, that there is a likelihood of reservoir-triggered seismicity. In this case of location, you should install a microseismic monitoring system. And it is important that you install it before construction to determine the background seismicity during reservoir impounding and during first years of operation. I would say after 10 years and so on, when you have no special seismicity, you could basically decommission these networks. So this is strongly recommended in areas with faults and high tectonic stresses in order to dispel any doubts about what is actually happening, because if something is happening, they will basically claim the owner of this project. This is a problem. Here, this is one reservoir, was the biggest embankment dam for some time in Iran, Zagros Mountains. There are plenty of faults, and probably like in the Himalayas also. And we see here this reservoir of the Karkhe Dam, and there were some monitoring systems which shows seismicity occurring around the reservoir. But as you see here, reservoir-triggered seismicity does not necessarily just occur at the dam site or in the reservoir, depending on the seismotectonics. It may be in the environment, and here a maximum event was recorded with a magnitude of 5.1. But you see there are plenty of occurrences of earthquake epicenters, but also these main faults, active faults and lineaments were known. They do not just occur along these tectonic features. They were occurring at this location. Okay, what I mentioned here, I take here another 5 minutes. A feature is, of course, I mentioned magnitude 5.7 and so on. There should not be a safety problem for well-built, well-designed, well-built, and well-maintained dams. But if you have a poorly constructed dam, like this one in Albania, already a magnitude 4.1 earthquake, with a peak count acceleration of less than 10% of gravity, it caused this landslide in the dam body. The reservoir is scarred to this large deformation. Of course, this was an existing dam. It's not a reservoir-triggered event here, but I just want to say if you have a new dam, which is actually poorly built, like this dam here, for example, then still moderate reservoir-triggered events could still create a seismic problem to your dam. But this should not be the normal case. This is a case in Pakistan, in Kashmir, there occurred a strong earthquake in Afghanistan with an epicentral distance of 300 kilometers and focal depth of 200 kilometers in April 2016, the magnitude 6.6. And it was after, I would say, after also heavy rain. And this big landslide, which involved 80 buildings, we do not really see it here, but many buildings here were moved down, was triggered by a very remote earthquake, 300 kilometers away. So therefore we can conclude, if we have a reservoir triggered earthquake in an area where your slopes are already quite unstable, safety factor of about 1, it could still create some big mass movement, as in this case here. It was 300 kilometers away. So mass movements are a problem, let me say, which could be triggered by RTS. Now, is RTS a safety concern for large dams? Just to answer this question, now we have to look in the seismic design criteria, which I mentioned last time. Basically, we have a dam and safety relevant elements, which are spillway and bottom outlet, and they have to be designed against the operating basis earthquake and safety evaluation earthquake. Okay, so these are the safety critical elements and the dam body, which are of main concern. And of course, in addition, we have the pertinent structures, which I have also mentioned. Now, what are the seismic performance criteria for dam and safety critical elements? The dam body, we said this is a repetition from last time. Under the operating basis earthquake, we say that the dam body is fully functional, only minor non-structural damage, which is easily repairable, is accepted. For the safety evaluation earthquake, we require that the reservoir can be stored safely, and structural damage, cracks, deformations are accepted. However, stability of a dam must be ensured. Okay, that is a traditional performance criteria. But if we look now into the safety critical elements, which are the spillway, gated spillway, and low-level outlets, we also require that they are fully functional under the OBE, and they are functional also under the safety evaluation earthquake, so the reservoir can be operated safely after an earthquake, because a repair may take a long time. Now, what are the implications on the design of this RTS? Since RTS occurs, let me say, for example, just during the first few years after completion of a reservoir, of a dam, we can say for a safety evaluation earthquake, the largest RTS event is actually smaller than the so-called safety evaluation earthquake. This is already per definition. So for the safety of a dam, RTS is, or for the people living downstream who may be afraid of uncontrolled release of a reservoir, RTS is not a problem, because the largest RTS is smaller than the safety evaluation earthquake used for the design and safety check. However, for the operating basis earthquake, where we make a statistical analysis, we say it is a probability of 50% in 100 years that it occurs. It has to be checked if RTS, which occurs, as I mentioned, just a few years, within a few years after completion of a project, we have to check if this RTS is larger than the OBE. If the OBE, if the RTS is larger than the OBE, when the operating basis earthquake, let me say a return period of 145 years, has to be replaced by the ground motion estimated for the RTS. So it has some effect on the operating basis earthquake. And for the appurtenant structures and buildings and infrastructure in dam and reservoir area that can be affected by RTS, you have to check if the so-called design basis earthquake given in building codes with a typical return period of 475 years. If the largest RTS event, it is very difficult to estimate that, I must say that, but if somebody feels he's able to do that, he has to check if this is actually larger than the design basis earthquake given in seismic codes, then this has to be replaced by the ground motion of the RTS event. So therefore, RTS, in terms of safety, it has an effect, may have an effect on the operating basis earthquake and on the design basis earthquake for buildings and infrastructure in the reservoir area. That is just for ground shaking. But and as we know already, ground shaking is affecting all structures at the same time. So if you look into the seismic safety or seismic design of your different components, sorry, of your power plant or of your dam project, you have to check if the design basis earthquake, which is used for design of some components, if RTS is bigger than that, or for the dam body and safety critical elements, if the OBE is, if the RTS event is larger than the OBE. So it has some effect on the design of, let me say, appurtenant structures and on the serviceability check of your dam and safety critical elements. So this is the effect, but it has no effect, this is important, on the safety evaluation earthquake, which is the most important issue for the safety of the people living downstream of the dam. Now, assessing, I think I can stop here and I will continue for the last few slides afterwards. We will stop here for the lunch break, and we will reconvene here in
1500 hours IST.
15 hours, okay. For me, it is 10:30 then in the morning. So if you can make a stop here until 15 hours.
Sure, sir.
Yes. Okay.
Sure.
We will
Thank you for
reconvene.
making an excellent and detailed presentation. We will now take a break for lunch and reassemble at 1500 hours IST.
Yes. Okay. Thank you.
Thank you, sir.